Now, it may seem weird that we are correcting for imbalance afterwards by evaluating the models. Isn't there a way that we can optimize our model parameters towards these minority classes? And yes, we can. This is called class weighing. It means that we basically give different classes a different weight. So in case of imbalance, it means we would give the minority class a higher weight. And this weight can typically be included in the loss function. For instance, in logistic regression, what we can do, we can add this class weight to our log loss function. So this means that, so the normal one would not have this, or the normal logistic regression would have all the classes have an equal weight. Right? If it's imbalanced, we can make, for instance, the imbalance for the minority class, we can set it much higher. We can make it like 100 times, give it more, 100 times more weight, which means that your optimization will now find a solution which gives more priority to those points. Right? This is a visualization. So here we have our original data set. So we have a minority class of white points and a majority class of black points. And we see that, well, because of the situation by default, it will learn sort of small shape for the white points, and some of the white points will likely be misclassified. If we want to avoid that, we can give more weight to the white class, and then we can see that now it's, yeah, you can see the decision boundary will be slightly changed, and we'll give more priority to this class. We can do the same with instances as well. So it means if we have certain instances, individuals really, which are likely going to be misclassified because they are outliers or they are deep inside a region where you would not expect it, but you know it's true. What you can do, you can give them more weight. And this is typically done whenever you have points which are somehow underrepresented. Right? So say you collect data, and it's biased in some way. For instance, you have, I don't know, you have some groups of measurements, and you know that some measurements will occur less in your data. You can add those points multiple times, but you can also just increase their weight. And that's called instance weighting. Right? So in that case, we give a weight to each individual point, no matter the class. Each point gets a weight. And then this instance weight will be used inside the loss function. So here for every point n will have a weight. And again, if that point has a high weight, its loss contribution will be higher than the other points. Right? And this is again visualization. So here we have this solution. If we increase the weights of some points, like this one here, because it's inside this other territory, so, but we want to give it more weight, or this one here, then you can see that now the boundaries stretch towards correcting these points, classifying these points correctly. So we can steer how the model will learn those points. And this comes up quite often in applications, that one class should get a higher priority, either because it's just less represented in our data while it's more represented in the real world, or it can be individuals as well, individual data points, which for some reason we cannot measure so much or so often, so they are less represented in our data, but we do want to give them more weight because they are expected to occur in the real world frequently. We can also more directly measure the cost of misclassifications or mispredictions by using some kind of cost function or by imposing some kind of external constraint. There are basically three different ways of doing that. The first is cost-sensitive resampling. So here we change the data set so that the cost of the predictions is reduced. We change the data set so that hopefully we'll get a better model with a lower cost. So one thing we can do is resample or reweight the data. Reweighting we've already seen. Resampling just means that you either oversample the minority class, right? So say you have one class which has very few examples, you can add the same example multiple times in the training sets. Or you could undersample the majority class. You could have just fewer examples of the majority class in your training set to correct this imbalance. Which one you should use depends a bit on the situation. Oversample the minority classes you can always do, but of course it does put a lot of emphasis on those points, which may not generalize as well as they should, right? So this does create some bias. Undersampling the majority class is generally safe if you have a lot of points at the majority class, but of course by not including training data, by removing training data, you may also end up with a worse model. So be careful about that. We'll get back towards other approaches towards correcting this imbalance in the preprocessing lecture. Another thing you can do is to increase the weight of the misclassified samples. So say that you don't have an a priori way to sample or weigh data points. What you can do is you can first build a model, see which points are misclassified, and then in the next iteration give them more weight so that the next model is more likely to get those points correctly. This is basically the idea behind boosting, which is an ensembling method that we'll discuss in the next lecture. Another more tricky approach is to decrease the weights of misclassified samples. So here the idea is that you build a very, very complex model, like a very large ensemble or large stack, very complex model, which is likely to give the correct predictions given enough data. But it would still make some misclassifications. And then you assume that those misclassifications are there because the data is inherently noisy. It can be label noise. Some points can be mislabeled or can be mismeasured, so their values are slightly off. So what you can do is decrease their weight or remove them entirely from the data set. So you build a very complex model, and if there are still points misclassified by it, you remove them from the data set. And the idea is that you remove the points which are likely noisy, and then you can retrain models on the remaining points. So you end up with a simpler model, which is less distracted by noise. This is generally called model compression. It's a general technique that you can use. But again, this needs to be handled with care and always think about the exact application you have in mind for this and whether it actually makes sense. You may actually want to inspect which points you are removing to see whether they are indeed noise points, whether they are indeed wrong, or whether you are removing good points. Okay, and a separate thing you can do is cost-sensitive algorithms. These are algorithms which inherently can handle different costs. One thing we've already seen, so you can weigh the classes, right? So if you have a minority class, you can increase the weight of that minority class so that the algorithm will have a larger loss if it misclassifies those. So it will be pushed towards not misclassifying points of those classes. More generally, some methods can also have a cost matrix. A cost matrix is basically, it's exactly like a confusion matrix. So it has for every possible class value in the rows and the columns, and basically it has a cost for every, it is actual and it's predicted. So if it's correct, then typically the cost is 0. But you can, for instance, say that if you predict class 1, so if you predict class 2 and it's actually class 1, this can be a cost of 1. While if you predict class 1, it should be class 2, maybe that has a cost of 1,000. Maybe that's 1,000 times worse than the other one. Okay? So you can sometimes supply such a cost matrix to your model. And a third approach you can use are cost-sensitive ensembles. These are methods that basically wrap your existing cost-insensitive classifier to make it cost-sensitive. One of these is meta-costs. What this does is it first builds a model, typically an ensemble, to learn the class probabilities. Right? So for every point x, it gives you the prediction of class 0 given x, the probability of class 1 given x, and so on. Right? So you learn this based on the first ensemble model. And then you relabel your training data to minimize the expected cost. Right? So if your expected cost is the probability to be predicted a certain class times the cost that occurs with that prediction. So if it's the right prediction, the cost will be 0. If it's the wrong prediction, then the cost will be related to how likely that model is to predict that point wrongly. Right? And then what we want to do is to relabel every data point so that this cost is minimized. This does effectively decrease your accuracy. Right? You're relabeling your data, right? So your accuracy will go down, but the idea is that your cost decreases as well. The second approach is ADA cost. This is similar to ADA boosting, which we'll see in the next lecture. So again, boosting builds a model, and then based on misclassifications, it will then reweight your data set, and next time builds a new model on the reweighted data. And so normally what you do is you reweight so that the misclassified points will be created correctly. In this case, we will reweight the instances to reduce the cost instead. And finally, we can also use these costs when we choose our decision thresholds. Right? So for instance, here we're looking at over a curve, and we want to know at which point we will minimize our cost. So we do that by first assigning a cost for each false positive and each false negative. For instance, maybe a false positive is 10 times worse than a false negative. Right? Then we set this to 1 and this to 10. And the total cost is the ratio of false positive times the cost of false positive times the ratio of positive examples in our data set, plus the amount of false negatives times the cost of false negatives times how many negatives are actually in our data set. If we do that, this yields different isometrics. These are these lines of equal cost. Right? So for a certain combination of false positive and true positive rate, this function here evaluates into a certain cost. And so we get this gradient basically. So in this case, the higher the false positive rate, the higher this cost gets. Now, we can set this trade-off. So say that false negatives are 10 times worse than false positive, then you will see these get very, very flat. And yeah, you'll actually find that the optimal solution is somewhere here. Right? So in this case, the false negatives are much more important than the false positives. So yeah, we don't care so much about the false positives, so we're happy with a high false positive rate. If we would actually want a solution which has low false positives, we can do the opposite. And now you can see that these lines become more vertical because we want a solution which has low false positive rate. Right? And for a certain ratio of the cost of false negatives and false positive, we will find a solution that corresponds to that. So the higher we make this, the threshold will change to a point where this cost is lowest for this trade-off in cost. Yeah, so you can basically set a certain trade-off between false negative cost and false positive cost, and then you do a line search over all possible thresholds, and you find the one that has the lowest value. Now, in some applications, you may actually want to use the class confidences. Right? So say that you have a self-driving car and it makes predictions with certain probabilities, like it's a certain probability it saw something or not. You may actually want to make decisions on that. So if it's a high probability, you do one action. If it's a low probability, you do another action. So this means that we need to trust the confidences that the model returns. And turns out we can't always do that. Right? So different models are good at giving class confidences. Others produce them, but they're not so good. Right? So especially SVMs and NF4s are known not to give good probability estimates. Now, to measure how good these estimates are, we can compute the Rsquared loss, which is simply the predicted probability, the difference between the predicted probability and the actual label. So this will be 0, 1, and this will be some value between 0 and 1. So say that you have a point and you predict it's 90% sure it's positive, so 0.9, and the actual label is 1, then that's good. You have a small contribution to the loss function. If, however, you predict 0.9 sure it's positive and the actual label is negative, yeah, that's a bad mistake. So that will contribute a lot to your loss function. So the lower, it's a loss function, so the lower is better. And so if you compute that for a few classifiers, you can actually see this confirmed. Logistic regression is a method that internally computes probabilities, right? It computes log loss. So this will typically give you good estimates. And we see that the Rsquared is on this toy data set 0.03, while the SVM has a Rsquared loss which is at least twice as large. Right? So SVM is much worse here. Luckily, there are ways to improve these predictions, and this is called model calibration. So we say that a model is calibrated if the reported uncertainty actually matches how often the model is correct. So say that these are all the probabilities that the model predicts. This is a histogram. So it predicts a lot of points with a low probability, some point with probability in the middle, and also a lot of points with a high probability of being positive. And so then we look at, we divide that into bins, divide 20 bins, and for all the points here, we measure how many of these are actually positive. If we say that if we predict a low probability and there are actually few positive samples in this set, then that's a good estimate, right? And so we do this for all bins here, and we look at the corresponding fraction of positive samples. If the predicted probability matches the fraction of observed positive samples, you will end up on this line, right? And that's a good calibrated model. Right? This is logistic regression again. So that gives you good predictions. So we see all the points end up near the diagonal, and we get also a very low Rsquared loss. On the other hand, perfecting machines, they look very different. So first of all, the predictions are more centered. This is partly because this is not a probabilistic classifier, so we have to translate the decision score. So we have to normalize it between 0 and 1. So by nature, they end up more close to 0.5. But separate from that, um, if we see what the corresponding fraction of positive samples is, we see that it's nowhere near the diagonal. Now, luckily, we can still fix this a bit. And the way this works is by first looking at the predicted decision values or probabilities, then passing these to a regression function, a calibrator, which will then have to map these to the correct outcome. Right? So we have our model, it gives you predictions, and we know what the correct predictions are, or the correct probabilities are. And basically we learn a function that maps these guys to these guys. Okay. This typically involves some internal cross-validation because we need to basically fit this regression model on this problem. And we typically do like an internal cross-validation with a few folds to learn the parameters for this. Right, so this is quite simply what we do. We take our original model, we take the outputs, we pass them to the calibrator, and the calibrator then returns to us the hopefully correct probabilities. And if you have a multi-class model, we require one calibrator per class. One of the most well-known methods for doing this is path scaling. And this is basically nothing more than using a sigmoid function. Right? So sigmoid function, we already saw this in the logistic regression lecture, but now we use it for scaling our probabilities. So basically, we take the predicted probabilities of our spectrum machine, we pass this to a sigmoid, and after we do that, hopefully our points will be nicely, or at least closer to, you will still see some kind of S shape here, so it's not completely solved, but it's a lot closer to diagonal than before. So this model is now calibrated. And the sigmoid, we have to fit that, right? So we look at all the predicted probabilities of the model for the negative points and all the predicted probabilities for the positive points. So we see it does make some mistakes, like all these are wrong and all these are wrong. But we fit a sigmoid through these exactly like as we did with logistic regression. And then this is a function that will translate these probabilities to these probabilities. A more general approach is called isotonic regression. It's the same idea, but instead of using a sigmoid, we use isotonic regression. And this is a method that basically what it does is say you have a bunch of points, and instead of learning a line through there, what you learn is some kind of function that has to monotonically increase. So it's more flexible. It doesn't have to be a straight line. The only requirement is that it increases all the time. So it either stays flat or it has to increase. So it's monotonic. Right? And basically, we learn this by learning a weight for every point in our training set. And then we learn basically a bunch of points, like here, these are points. And then if we have to make predictions, we just interpolate between those points. And we see it in this case because this is a perfect machine, it has this S shape, so it also approximates this S shape as well. But it doesn't have to, right? So while the sigmoid can only really work for cases where this curve looks like an S curve as well, isotonic regression works, basically it fits towards any possible shape of probabilities that you may occur. So it's a lot more flexible, it's a lot more generally useful than path scaling, but it's also more flexible, so it tends to overfit, especially on smaller samples. Okay, finally we have a few other metrics that we should probably mention. First of them is Cohens Copper. So Cohens Copper is basically measures the inter-rater agreement. So say we have a model 1 and a model 2. And they both make predictions. Basically, what we do is we measure the agreement in predictions between those two models. Now, if you have a single model, we just take our original model, and then the second one is a random guesser. It's a random guessing model. So it just randomly guesses the output, and then basically measure how much agreement there is between our model and a random guesser, right? Basically, it looks like this. So our kappa score is the accuracy of our model and the accuracy of a random classifier divided, normalized by 1 minus a random classifier. Because of course we want to do the opposite of what the random classifier does. If you want, you can also weight this, so you can give different misclassification, different weights. So say you have 3 classes, class 1, class 2, class 3. You can say, for instance, that misclassifying class 1 as class 2 is not so bad, but misclassifying class 1 as class 3 is worse. So you could also include that if you want to. And a second method that's often used for imbalanced data is to make use correlation efficient. It's not super popular in most machine learning research, but it's quite often used, for instance, in biology. Okay, let's now turn to some regression metrics. First of all, the most commonly known one is the mean squared error, or the root of this, which is simply this, is the root mean squared error. This is simply the predicted value minus the actual value for every point and it's squared. And another way of doing this is to take the absolute value between the prediction and the actual value. And this is called the mean absolute error. The main benefit of this is that this is less sensitive to outliers and large errors. So say that you have some points and you learn a line through there, but there's an outlier here. Right? So in case of mean absolute error, the contribution of this point will simply be this difference. If we use the mean square error, it's this difference squared. Right? So this one point, this one outlier, will have a massive effect on the evaluation of this model. And we may not want to pay so much attention to outliers. So in that case, the mean absolute error is a better measure. Now, one drawback of both the root mean squared error and the mean absolute error is that they are basically unbounded, right? So the lowest value is 0, but the largest value can be infinite. So there's no way to interpret. So if you have an RMSC of 0.05, what does it mean, right? So an easier interpretable measure is R-squared. What this does is basically measure how much better your model is than just predicting the mean. Right? So if you have a bunch of points, hopefully you will learn a function like this. And that gives you a certain R-squared score. And what it does is it basically measures how much better this prediction is than just predicting the mean through all these points. Right? So it's a relative performance measure. This is nice because now it's between 0 and 1 usually, right? So 0 means that you do the same as the just predicting the mean, or you do as good as predicting the mean. If you have score 1, you do a lot better than, you basically have perfect predictions, right? And if it's negative, it means you're doing worse than the mean prediction. So that's bad, right? Your model is basically doing worse than just predicting the means. That's the worst you can have. And it's actually unbounded in the negative. So it's possible to be minus 2 million. But yeah, any negative value is bad. So you compute this by the ratio of 1 minus um, basically the sum of squares between your predictions and your functions. It's the sum of these guys, the blue squares, divided by the sum of squares of the mean prediction. Right? So in this case, well, the mean obviously is worse than my model. So hopefully I will get, so this value will be much larger than this value. So hopefully this will stay close to 1. This is a very intuitive method to interpret. Finally, we can also visualize the regression errors and that way get a better view of which points are misclassified or how, basically what the model is actually doing. The most common way of doing this is the prediction plot. This simply predicts the predicted values versus the actual values, and hopefully all our points are on the same line. But in this case, for instance, we see that it's doing a pretty good job for most values, but if your true values are high, then your model is not doing so well anymore. Right? So you can interpret that from this plot. A slight variation of this is the residual plot, which is the truth value versus the difference between the truth and the predicted value. And yeah, this gives you slightly more interpretable plot. So here again, you see that as the true value gets higher, the error basically gets a lot higher as well. Now remember in the beginning when we talked about cross-validation, and if we evaluate a model n times on n different trained test splits, we could look at the average, but we could also look at the variance, which is how much variation there is between models. Maybe on one trained test split your model does very well, and on another trained test split your model does very badly. We can actually do some analysis on that to better understand what kind of misclassifications your model is making, and from that get a better insight in whether it's overfitting or underfitting, or whether there's some kind of weird behavior going on. Now we can do this by something called bias variance decomposition. What this means is that we decompose our errors into either bias error and variance error. The bias error are all the points that are systematically misclassified. So say that I train my model on 100 different training samples, some points will be always misclassified. That's my bias error. They're predicted equally wrong every time. If, however, you have some points which are sometimes predicted correctly and sometimes incorrectly, depending on the exact training set, then that's a variance error. It means that your model is inherently a bit unstable. It's easily influenced by having slightly different training samples, and this then yields different predictions. So graphically shown, it means that if your model, so these different points here are is a score basically of your model. You want to be in the bullseye. It's the score of your model by simply training it on different training sets. Right? So if we train this model on different training set samples, and every time we are giving the correct predictions, then we have low bias, low variance. If, however, we make predictions which are never really good, but somehow close, but yeah, there's a lot of variation there, then this is low bias and high variance. If, on some cases, we have some points which are always misclassified, no matter what the sample is, this is high bias. You systematically make the same mistake over and over again. And you can even have situations where you have both high bias and high variance. So you're off the mark and you also have a lot of variance. Okay, how do you compute this bias and variance? Basically, you take 100 or more bootstraps, or shuffle splits if you like, and then for regression, you look at each individual data point. and then you measure the difference uh, between. So if you have 100 predictions, you compute the mean, and you look at the difference between this mean and the true expected output. That's your bias. Right? And the variance is simply how much variance there is in these predictions. For classifications, we again look at each point, which is again, each point is predicted a number of times. Right? And the bias there is simply how many times this point is misclassified every time it occurs in a test set. And for variance, it's a bit more complicated. We look basically at what's the probability of having class 1, what's the probability of having class 2. But if these are like in the middle, then the squares of these will end up with lower sum. If you have like one of these is very high and one of these is very low, this sum will be slightly higher. So if these predictive probabilities vary a lot, then this yields high class variance. And the total bias is simply the sum of all the biases you found for every point times the weight of the point, and the weight of the point is how many times it occurs in the test sets. Right? So you have 100 samples, so on average it will occur by 30 times, 30% of the time in the test set. So that's this WX. And same with variance. Okay, now more importantly is what this means for unwritten overfitting. So in a cartoonish way, high variance means you're overfitting. It means that you probably have a very complex model that's easily influenced by having slightly different training data. Right, so if you measure high variance, typically it means that your model is overfitting and you should regularize it. You should make the model simpler so that it becomes more stable. If, on the other hand, you observe high bias, it means you're likely underfitting. Your model is too simple and cannot capture the concept you have to learn accurately. Right? So you have to make your model more flexible. Now, if you look at some actual data and some actual bias variance numbers, we can better understand what regularization really does. Right? So look, for instance, at this support vector machine here. And remember, the C parameter is the inverse of the regularization strength. So on the right, we have low regularization or high overfitting. Now, if we increase our regularization, what this does is effectively it reduces the variance without changing the bias initially, right? So we see as we decrease C, as we regularize our model, we can see that the variance error goes down, and that's why our total error goes down as well. However, at some point, if you regularize too much, our bias error goes up. Right? Now the model becomes too simple. It's unable to learn harder points in your training set. So then the bias goes up. And yeah, same thing with logistic regression. If you have overfitting on the left, on the right, regularization will decrease the variance. It will keep decreasing the variance, but at some point the bias will go up. And that's why you have this very typical U shape in your data, right? So at first, your test set error goes down because the variance goes down, but at some point, the test error goes up again. That's because your bias error takes over. So that's why you get this U shape in here. And so if we bring all this together, we get this nice summary flowchart by Andrew Ng, which is a handy guide for how to change your models so you get better performance. So first of all, you can start training, and after a while, you observe your training error. Now, if your training error is high, it means your model is biased. And there's different things you can do about that. So one thing could be just to train longer. Right? So if you have your learning curve, if this is the number of training examples you have already seen, assuming you have a very large data set, and this is the loss of the error. It could be that you still have a high training error, and by simply trying more, eventually you will still go down. The loss will still go down. That's option one. Option two is to have a more complex model. Like you can try kernelization, or if you have a neural net, you can add more nodes or more layers to your network. You can also obtain more features. If you can add more descriptions about your data, or you can use something like kernelization. Like kernelization also effectively adds more features to data, makes it more flexible. You can also decrease regularization. So if you have a regularization parameter, you can relax it, so your model is less likely to underfit. Or you can try an entirely new model architecture. Just play around with different architectures, different models to see if that helps. However, if you have a low training error, but you have a high test error or high consolidation error, you're likely underfitting and you're likely overfitting and you have high variance. So it could be that you don't have enough data, so obtain more data if possible. You can also select features because that makes the model less flexible and maybe less overfitting. You can definitely increase regularization. So most algorithms have a regularization parameter that allows you to control the complexity. Or again, you can try another model and see if that works better. Okay, so after you've found the best evaluation metric to evaluate your models, we can use this to tune our hyperparameters. Typically, most models have some hyperparameters we need to tune, or we need to decide which preprocessing to use, and for that we can basically try different models and see which is the best setting. There are different techniques to do that. The most commonly known are quick search and random search. Quick search is shown here. So this means that for every hyperparameter, so let's say this is hyperparameter 1 and hyperparameter 2, and then for each hyperparameter, we need to discretize it. We need to choose a limited number of values that we want to evaluate, and then we evaluate every possible configuration, every possible combination of these. So every point here is one configuration. It's one value for each hyperparameter. Of course, if you have many hyperparameters, this will lead to a combinatorial explosion. That's one problem. So it doesn't really work if you have many hyperparameters to tune. And second, because you need to discretize your data points, you may actually miss the optimals. Maybe this is the optimal and you missed it. So say that the optimal is somewhere here. You missed it because you had to discretize some way and you had no prior information about where this optimal will be. Random search, on the other hand, just randomly picks points. And this seems like a less systematic approach, but on average the results are much better. One of the reasons is that, well, it scales much better, right? So if you evaluate 100 points for 2 hyperparameters or for 5 hyperparameters, it's the same amount of time. You can easily control how many points you want to evaluate. You can even track over time to see what's the performance of the best model, and if you're happy with that, you can just stop, or you can keep looking for better models if you have more time or more budget to spend. The second reason why random search works so well is that most often some hyperparameters are more important than others. They have a larger effect on performance. So say, for instance, in this case, we have our hyperparameter 2 here, and in red here, we show the corresponding performance. So we see that by changing this hyperparameter 2, this has a big effect on performance of a model, while hyperparameter 1 has a very small effect on the performance of a model. Right? So tuning hyperparameter 1 isn't worth so much. Right? we should focus more on hyperparameter 2. Now, we may not know this beforehand. We could actually test this beforehand, right? But typically, we have no guarantees that on our new data set, this hyperparameter will be important or not. So in that case, random search is better because by evaluating random points, we actually have evaluated many points for hyperparameter 2 here. Right? We have many points here, while grid search has only evaluated 5 points. Right? For these reasons, random search is typically preferable whenever you have a many hyperparameters or p, your hyperparameters have different effects on performance, and some may be more important than others. Now, grid and random search are by far the most commonly known techniques, but there exist actually many more advanced techniques. And we'll get back on that in the lecture on automated machine learning, where we will not only tune the hyperparameters, but we will also optimize the preprocessing steps or the neural architectures that we want to try. So we completely automate the search for the best possible model. Now, you need to be a bit careful when you optimize your hyperparameters. The best way of doing this is to take your data set and to separate that into a test set and a training set. Now, we want to train our best model on a training set and a test on a test set, but first we need to find that optimal model. So we do that by first defining our hyperparameter space. This could be your grid search or your random search. And then we try each hyperparameter on our training set. Now we can't use the whole training set, right? Because if we would evaluate every configuration on training set, we have nothing to test it against, and we cannot touch our test data set. So what we do is we do an inner cross-validation. So we take our training data and we build different cross-validation splits on that. Every hyperparameter we will evaluate on all the folds, so we get 3 scores again for each hyperparameter, and we take the average score as a score for that hyperparameter. And then after we do that for all the hyperparameters in the space, or until we decide to stop, we take the model which has the highest average score, and that's our best hyperparameter. Now, if we have found that, then we retrain our model with the best hyperparameters on the full training set. That's our best trained model, and then we test it on the test data to get our final evaluation. Right? Now, in the simplest approach, we have a single test data set. But of course, the way you split the training and test data is again a source of sampling bias, right? So ideally, we want to make this split multiple times. Right? That would mean that we end up with not only an inner cross-validation, which we use to tune our hyperparameters, but we will also have an outer cross-validation over the entire procedure. So, yeah, and the reason why we want to do that is that if we have like a single test set here, we will end up with hyperparameter values which work best for this specific training data set. Right? So it's likely that we will overfit our hyperparameters on this specific training data set. And if you would have a different split, we may end up with very different hyperparameters. Now, to avoid that, we can use a nested cross-validation, right, in which we have an outer loop. So we have our original data set, and in our outer loop, we build different folds with cross-validation fold 1, cross-validation fold 2, cross-validation fold 3, and so on. This will consist of train and test. We then separate this training set again in inner cross-validation 1, inner cross-validation 2, inner cross-validation 3. We evaluate our hyperparameters on these. After we found our best hyperparameters, we retrain our model on the full training set and we test on test data set, and that will give us the first cross-validation score, which is a score of the best hyperparameter setting we found in this split. And we do that n times, and then we take the average of that, and that would be the score of our tuned model. Now, important is that the best hyperparameters can be different in every test set. So we'll end up with a set of course validations. We end up with a set of hyperparameter settings, each with a score, and you can look at the average score as a measure of how good our optimized model will behave. And if we would actually want to use this in practice, what we would need to do is to forget all this again, and then basically retune our hyperparameters with an inner CV. Right? We can split, and in the end we end up with the best hyperparameters that we obtained on our full data set. So now we don't have to test it anymore. We found the best hyperparameters on a full data set, which we hope will then work well on future data. Right? So the nested cross-validation looks a bit like this. So I have a random search here. This is my base model, supervector machine. So I want to tune the hyperparameters of this guy. My hyperparameter space consists of C and gamma, both varied on the exponential scale. I use an inner threefold CV. And so this will do a random search for a specific training set. And we wrap this inside a cross-validation procedure, which will do an outer 5-fold cross-validation given all our data basically. And then from that, we will get a list of scores which we then can average. All right, so we covered a lot of ground. It's time to summarize. So first of all, we need to split our data into a training and test sets according to the application, which means that we need to define test sets as if they would occur in the real world. There's some rules of thumb. First of all, if we have a large data set, we can use a holdout, which means we randomly select points for a training set. If our data set is smaller, this may cause a sampling bias. So we want to use cross-validation instead, so that our trained test splits are better defined. And ideally use something like n times scale cross-validation if you have the compute and time for that. If you have very small data sets, it's better to use leaf-without cross-validation. Whenever you do classification, always use stratification. It's a simple rule, but it's sadly often forgotten. If you have group data, which means you have multiple rows in your data set that belong to the same group or person, you want to have these either all in a training set or all in a test set. So for that, you need to do a grouped cross-validation. If your data is ordered, like a time series, always make sure that your older data or your previous data is in the training set and your newer or next data is in the test set. Okay, once we have split our data, we have to choose a metric that fits the application. For instance, if we have to avoid false positives, we can use precision. If you want to avoid false negatives, we can use recall. We also saw other metrics, such as the F1 score. If we have probabilistic predictions, we should use them, and we don't have to stick to the default thresholds, and we can actually tune them or calibrate them to fit the applications. Right. For instance, if we care about false positives, we may want to increase the threshold so there are fewer false positives, typically at the cost of also losing some true positives. Now, to find the optimal threshold, we can use ROC curves or precision recall curves to look at the shape of the curve and then see where the optimal thresholds lie. And we can also use this to decide between different models. If you have one algorithm which gives us a certain precision recall trade-off that another algorithm cannot offer us, then we should use that model. If possible, always include costs into risk classifications. So there's different ways of doing that. So either we include some costs somehow internally, and we can use class weighting, so we can give classes different weights. For instance, if you have a minority class, we can give that minority class a larger weight so that the training is forced to get those points more correctly. Or we can also do instance weighting. If we know that some points are likely to be classified or they're important to get right, we can give those instances a higher weight so that again our model is pushed towards predicting these points correctly. And if there are costs involved, we can plot the ROC isometrics and see how this will translate into the optimal threshold for the costs that we have in mind. Again, be careful with imbalanced or unrepresentative data. If your data is biased and somehow you can use class weighting or instance weighting, or you can under or oversample your training set to correct for these issues. Whenever you intend to use the probabilities of your models in your applications, you need to be able to trust them. Right? So for some models, you can do that. Like logistic regression, you can just use those probabilities. For other ones, like supervector machines, you cannot, and you should calibrate the models so that the probabilities they predict are actually relate to the expected amount of positive and negative cases. And if there are hyperparameters, and there are typically always hyperparameters, always tune them. Some algorithms have really good defaults, but you have no guarantee that these defaults will work well on your dataset, so always tune your models. Now, if you tune your hyperparameters manually, you can use your insight. You can think about what causes bias, what causes variance in your models, and use that. So if you see that your model is overfitting, you can do whatever you can to reduce the variance error. You can regularize, or you can also think of other ways that you can reduce variance. If you see that your model is starting to underfit, think of ways you can reduce bias. But these days, of course, things get more automated, and there exist many hyperparameter optimization techniques. We'll go back to this later on, but for now, just be careful that you don't overtune, because the more you can keep doing this, you can keep optimizing, but at some point you will overtune on your train test bits. You can do it in nested CV to avoid that a bit, but in general, always be careful not to take this too far. Right, that's it. Thank you for your attention, and hope to see you in the next lecture.